Hi, welcome to Dissolve Chemistry. Let us continue our discussion with Mission 7070. In the previous video, I have given the knowledge that how this mark distribution is done according to the chapter and how you can choose the chapter and how you have to study to score easily 70 marks in chemistry in the board examination. Okay, so here we will start with the first unit, that is solutions, and we know that its weightage will be 13 marks. And that 13 marks is divided as you will be getting 1 mark questions 2 and 2 mark questions will be 1, and then 3 mark questions will be 3. Out of that 3 questions, 1 will be of theory and 2 will be having numerical problems. Okay, and overall it comprises 13 marks. Now let us look into, we will recap in its upcoming next 40-45 minutes. First one, we will take a definition of the term solution. So what do you mean by solution? It is an homogeneous mixture of, homogeneous, you should remember, homogeneous mixture. What do you mean by this homogeneous mixture? So that after dissolving 2-3 components together, you cannot differentiate, means it will be uniform throughout. Say for example, you can take, if you take sugar, okay, and plus salt plus you take water, means you add sugar and salt to the water, and if you dissolve, then you will be getting a clear solution, and that clear solution is nothing but what? Homogeneous mixture, where you cannot differentiate between the phases. Or that solution, how we are going to define? Homogeneous mixture of 2 or more components. Here already I have taken 3 components are there. Okay, and sugar, salt and water, these 3 are called as what? Components of the solution. Components of the solution. Okay, you should remember this. So now this based on the quantity of the components of the solution, we are categorizing, means we are dividing that solution into 2 parts. One we call it as what? Solute. Okay, and another one we call it as what? Solvent. Both will lead to what? Overall we call it as what? Solution. Then what is this solute? Solute is any component of the solution which is in a lower quantity is said to be solute, and any component of the solution which is in larger quantity is called as what? Solvent. So then larger quantity solvent, smaller quantity solute, and both put together we call it as what? Solution. Okay, I hope you have understood. So now there are many different types of solutions are there. Okay, so we will go with that. Just I will give one example because it is 1 mark question, very important. Okay, so we will take into account of this. Based on the type of solute and solvent, okay, we are categorizing these solutions into various types. We will take fast rapidly. Okay, solvent we will keep it as what? Solid. Say for example, solute as your gas, then we will take liquid, then we will take what? Solid itself. Okay, so then the example for gas solid will be gas adsorbed on the surface of a charcoal or metal, you can take as an example. Okay, why I am going with detail with this is because we will get question on this. 1 mark questions will be there on this. Okay, gas adsorbed over charcoal is an example of mercury with other metals like make sodium, or you can take palladium or anything. Okay, so amalgams. So where any compound it is mixed with the mercury, we call it as what? Amalgam. Okay, solid you can take example, many alloys you can take, alloys. Say for example, steel is an example, right? So where the solvent means which is in large quantity is solid, and small quantity will be solid or liquid or gas that we have taken. Okay, so these are the 3 different types. Then once again we will take your solvent as liquid. Okay, and then your solute will be, say for example, gas. Normal water will be having what? Dissolved oxygen. dissolved gases in water. Okay, water contains oxygen, nitrogen. Okay, small quantity even carbon dioxide will be there. Okay, so that are the examples, or even you can take HCl solution. Okay, so HCl is a gas actually. So when you dissolve it in water, it will dissociate to give H plus and Cl minus. Anyhow, so it is a solution. Okay, which is gas liquid we can give. Next is after this liquid. You can take a very good example is ethanol solution. Okay, of various proportion you can take, right? Ethanol solutions. Then next is liquid is over, then followed by that solid in liquid. Already we have discussed that is sugar solution, salt solution. All these are the examples for that. So next we will talk about solvent is gas. Okay, so your solute will be, say for example, gas we will take. So mixture of gas, atmospheric gas we can take as an example. So where you will be having what? Gas means nitrogen is mixed with dioxygen, carbon dioxide and many other gases we can. Then next is liquid in gas. Okay, so your mist blower. Okay, mist is an example of gas mixed in the liquid mixed in the gas. Okay, the next is solid in gas that you can take. So iodine or camphor. Okay, in gas is an example for what? Solid in what? Gas. So this is how you should remember the examples, because this is very important for 1 mark. They may ask any one of this example. They will ask generally solid, gas, liquid, or anyone. So they will ask for a given example for, say for example, gas in solid, okay, solution, right? So like that question will appear, and this is very important for 1 mark. Okay, make note of this, right? So after this types of solution, the next important point is that expression of the concentration of the solutions. Okay, so again it is also one of the important bit, and you will be getting many questions on this expression of concentration of the solution. Okay, so we are going to express in different ways. Okay, so what do you mean by the concentration expression? Meaning is what? So the expression of amount of solute per given quantity of solvent, that we call it as what? Expression of the concentration of the solutions. Okay, there are various ways of expressing the concentration in different field. They are going to use in different way. So we will see that one, and again it depends upon even concentration also. If it is very dilute, we are going to use a particular unit for the measurement of the concentration. So we will see that. Okay, the first one is percentage composition. Okay, so this percentage composition we will express in terms of weight by weight. Okay, so weight by weight meaning is what? See, all will be multiplied with 100, because we are saying that percentage composition. So what do you mean by this solubility? Let us understand. So solubility means any solvent you take and any solute, you are taking solute and you want to make a solution and you are adding to the solvent. The extent of solute that can be added to the given amount of the solvent. Okay, so amount of the solute, maximum amount of the solute that can be dissolved in a given amount of the solvent is called its solubility. Say for example, I took 1 liter of water. Okay, so 1 liter of water means fixed quantity of the solvent. Then how much amount of the sugar I can dissolve in this? Maximum I am asking, maximum, to greater extent. So that we call it as what? Solubility of a given compound in a given solvent. Mass of the solute by total mass of the solute divided by total mass of solution into 100. We call it as what? Weight by weight expression we call. Okay. Similarly, second one is B. We call it as what? Weight by volume. Okay. Volume, it is also represented W by V. Okay. So total mass of the solute to the volume of the solution into 100. So that we call it as what? Weight by volume. How we are going to express the amount of the solute present in the given volume of the solution, we call it as what? Weight by volume per 100. That is percentage we call, right? Similarly, last one we are going to express in terms of volume by volume. Volume by volume. And how it is being expressed? So generally liquid, if it is there, both are liquid, then we are going to express this one. So volume of solute to the total volume of the solution into 100%, we call it as what? Volume by volume expressions. Okay. Then second unit what we are going to use, important one, is that molarity. So this is a very important which we use in chemistry. So molarity means number of moles of solute in 1 liter of solution is called molarity. We call it as what? Mole per dm cube is its unit. Dm cube or liter, mole per liter. Okay. So that is what is nothing but what? Molarity we are going to express. Then next is molality. Okay. So this we represent, it is M, capital M, and it is small m. So number of moles of solute divided by per kg of solvent, kilogram kg of solvent, per kg of solvent, we express as mole per kg. So then it is called molality. Okay. Then next is mole fraction. So how do we express this mole fraction? Mole fraction means, so it will be the number of moles of solute or any component of the solution, number of moles of a component, okay, any component or solute to the total number of moles of solution. Okay, so that we call it as what? Mole fraction. Similarly, if you have lower concentration, very low concentration, if you have, that we express in terms of what? Parts per million. This is also very important. Many times they have asked in the examination parts per million. Okay, what is ppm? Expand ppm. Okay, so like that they have been asked. So this is one thing you should remember. It is always used to express very low concentration. So it is equals to what? Number of components in grams or in milliliter by total number of components present in the solution, okay, into 10 to the power 6, then it is called ppm. Okay, so that is how we are going to define parts per million. Okay, so these are the important units in which we are going to express concentration of the what solutions. And on this particular topic you will be getting 1 mark question, or sometimes you may get one numerical problem on this. One numerical problem we will be having on colligative property, another numerical problem will be either on these concentration expressions or on the Henry's law. Okay. So what do you mean by this solubility? Let us understand. So solubility means any solvent you take and any solute, you are taking solute and you want to make a solution and you are adding to the solvent. The extent of solute that can be added to the given amount of the solvent. Okay, so amount of the solute, maximum amount of the solute that can be dissolved in a given amount of the solvent is called its solubility. Say for example, I took 1 liter of water. Okay, so 1 liter of water means fixed quantity of the solvent. Then how much amount of the sugar I can dissolve in this? Maximum I am asking, maximum to greater extent. So that we call it as what? Solubility of a given compound in a given solvent. Okay, so let us go into that. So we are expected to discuss solid in liquid, what factors are going in that solubility and all that. We will see that one. This is also very important. We'll consider solid in liquid solutions, which is one of the general and generally we perceive and we come across with, like sugar solution, salt solution. Okay, so generally like a base solution, NaOH, if you dissolve in water, okay, alkali solution we get. So all these are the examples of solid in liquid, and which is very common. Generally we have the perception as a solution means solid dissolved in liquid. Okay, solute in a given solvent, right? We will take water and we want to dissolve sugar, right? So now first thing is how much amount of the sugar I can dissolve in a given quantity of the water depends upon what are the factors that we will see. First one is we call it as what? Nature of solute and solvent. Say for example, polar solute is there and polar solvent if it is there. So therefore they are readily soluble with each other. Right? Similarly, non-polar is soluble in non-polar. If the solid is non-polar compound, then the liquid is also non-polar, then readily they are miscible with one another. So what is the reason for that? Say for example, water is having what? Dipole. Okay, partial positive charge, partial negative charge. So it is a polar. Because of this reason we call it as what? It's a polar. So now suppose if you dissolve non-polar compounds, right, like methane, if you want to try to dissolve it, so it is insoluble because it is non-polar. So it is having partial charges. If that also solute also has the partial charges, then readily it is soluble in water. So if it is not having, it is not possible. So therefore like dissolves in like. So therefore polar compounds are soluble in polar solvents and non-polar compounds are soluble in non-polar solvents. Okay, so you should remember that. That is solute, nature of the solute and solvent. And second point is that depends upon the temperature. Okay, the one is it is going to depend upon enthalpy of mixing. Okay, so if the enthalpy of mixing means upon mixing the solute and solvent, if heat is evolved, exothermic, so then by decreasing the temperature, okay, so we can enhance what? Solubility of the solute, sugar, solid solute in solvent. Okay, so then if the enthalpy of mixing, okay, so it is less than 0, we call less than 0, then it is said to be exothermic, and decreasing in temperature leads to what? Increase in the solubility of the solute. Then enthalpy of mixing is greater than 0 means endothermic. If the process happens with absorption of the heat, So then if you rise the temperature, you can enhance what? Solubility. Okay. So you can enhance the solubility. Say for example, sugar, if you want to dissolve, by raising the temperature, you can enhance the solubility because it is endothermic process. Okay. So that is how the nature of the solute and solvent, temperature, and third one is again enthalpy, which is going to decide the temperature factor. And third important one is pressure we call, and this pressure has negligible or no effect on the solubility of solid in liquid. What is the reason for that? Non-compressible, so therefore pressure is not having any effect on the solubility of solid in liquid. Okay, so this is all about a solid in liquid, and next we will talk about gas in liquid. This is very important. Okay, so once again they may ask what is solubility, discuss various factors. Okay, make note of this question. Okay, it may appear for 3 marks. Theory question is there, no one theory question. So they may ask what is solubility and discuss various factors which are responsible for the solubility of a given compound. Okay, so next is solubility of gas in liquid. We will take gas in liquid. This is very, very important. One question will be there on this particular topic. Here we come across with one important law, that Henry's law. We will see that one. Okay, so gas in liquid. If you want to solubilize gas in liquid, so how the factors are going to affect us, so that we will see. The first one is nature. Once again we will see nature of solute, that is your gas. Okay, and nature of your liquid, that is your solvent. Once again the same generalization we can make out here, so that like will dissolve in like. Say they, for example, you can take non-polar gases like dinitrogen, dioxygen. Okay, these are least soluble in water. What is the reason for that? Least soluble, because water is polar but these gases are non-polar, so therefore what? It is least soluble in water. Similarly, if you take, say for example, carbon dioxide, okay, and you can take ammonia, and you can take HCl. So these are readily and to greater extent they are soluble in water. What is the reason for that? These are all polar and your solvent is also polar, so therefore they are polar interactions will be there. So because of that reason what? So these are readily soluble in water. Okay, so that is how the nature of solute and gas and liquid we can take into example, right? So these are the things how we have to explain this particular point. The next is temperature. Okay, we can make the generalization here. So temperature, of course, it is having very important role in the solubility of gas in liquid. So how it is going to affect is generally the solubilization, or when you dissolve the gas in water, so then what happens? This process is said to be exothermic, means enthalpy of mixing is always less than 0. So therefore, by increasing the temperature, there will be a decrease in dissolution of gas in a given liquid. So therefore, by rising the temperature, okay, thus rising the temperature, solubility decreases. Okay, by decreasing the temperature, we can enhance the solubility of the gas. So that is how temperature factor we can explain. The next important is pressure. Okay, so we'll see that one. Next is pressure, the effect of pressure on solubility of gas in liquid. We will see. See here, the solubility of the gas. Okay. The solubility of the gas in a given solution, okay, increases with rise in pressure. If you raise the pressure, if you compress the gas over the surface of the liquid, so then what happens? Its solubility into the, or getting gas into the liquid phase, also enhances. And you should remember this solubility is in what? Is going to attain an equilibrium. Okay. So as you go on compressing the gas, then what happens? Solubility enhances, and it is being given by Henry's law. What Henry's law says, this is very, 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 very important. You make note of this. 1 mark question may appear, or 2 mark, or 3 mark. All the 3 possibilities are there, and in that 1 question will be there on this particular topic. Okay, without that it is not possible. Maybe 1 mark, maybe 2 mark, maybe 3 mark. But 1 question will be there on this. Very important, you should not leave this one. Okay, so the amount of the gas dissolved, okay, that is dependent on the partial pressure, okay, of the gas is directly proportional to mole fraction of the gas over the surface. Okay, so P is equal to KH into what? Mole fraction of the gas. That is, so the partial pressure of the gas over the surface of the solution is always directly proportional to mole fraction of the gas which is present in the given solution. Or we can say that, so the amount of gas dissolved in a given solvent, that depends upon the what? How much pressure you are applying over it. Okay, so like that also you can understand. Here KH is your Henry's constant, and P is the partial pressure or the pressure what you are applying over the surface of the gas, on the gas over the surface of the liquid, and here Xg is the mole fraction of the gas. Okay, so mole fraction of the gas, right? And a very important thing is that its applications. Okay, so the applications of this Henry's law are, the first one, the questions will appear on this, very important. You should remember, already I have told you. So they will ask, state Henry's law and mention its application, 3 mark question. Okay, so mention any 2 applications and state the Henry's law, 2 mark question will appear. Or just they will ask the definition of the Henry's law, or some applied questions will appear on this particular Henry's law. You should remember that. The first important thing is that application is that in the preparation of what? Carbonated drinks. Okay, so here we are going to use the Henry's law to dissolve more amount of the gas in water. Carbon dioxide is dissolved in carbonated drinks. High pressure, the carbon dioxide gas is packed into the what? Liquid, that is water, we can say, right? So that is what is one of the application. And second application is in scuba diving is that what in deep sea when they go, okay, so there what they are going to use, they are going to use oxygen cylinders, and these oxygen cylinders generally what it is being mixed with dinitrogen and oxygen will be there in that gas. So now when you go into the deep sea, okay, by the scuba divers, so when they go into the deep sea, there what happens, the lot of pressure will be there. So then what happens, large amount of the nitrogen gas will dissolve in blood. Okay, so actually the dinitrogen is being used for what purpose? To dilute the oxygen. So now the dinitrogen concentration increases when you reach into the deep sea, and as you come out, okay, immediately the pressure will be reduced, and that release in the pressure leads to what? So sudden there will be what? The nitrogen gas wants to escape out as the pressure is being relieved. So therefore that leads to what? Air bubbles are created in the blood vessels, and that leads to what? Narrowing of the blood vessels. We call it as what? Bends we call, and that bends are very painful. Okay, so therefore according to this Henry's law, what it is being done, so a inert gas like helium is being used to dilute the oxygen rather than dinitrogen. Okay, helium is also mixed, right? So that is another second application. Third point what we can make note of this is that if you go to the high altitude, so there we find that there will be a low pressure of the gas we are going to observe, and there will be a low oxygen, blood oxygen we can call, and usually that leads to what? Tiredness. Okay, the climbers, those who go on the top of the hills, so generally they feel fatigue, or we call it as what? Tired, and there, due to what? Low oxygen level at the what? Hills. Okay, right? So this is the third application what we can see. From Henry's law we can predict all these things, right? So you should remember this Henry's law is very important. At least you will get one question from this, either 1 mark, 2 mark, or 3 mark. Okay. So vapor pressure. Okay, what do you mean by this vapor pressure? Any liquid, so it will be covered with its own vapors. Okay, means the molecules of some of the solvent molecule escape out and they will take gaseous form, and that we call it as vapor of that particular liquid, and they are going to exert the pressure over the surface of the liquid, and that we call it as what? Vapor pressure. Okay, so now this vapor pressure, right? So of two different liquids, if you take mixture of two liquids, say for example it is a liquid A, and if you take a liquid B, okay, so it will be having its own vapor form. That depends upon its boiling point or its nature, that how much amount of the vapor will be there at a given temperature, say 25 degrees Celsius, liquid B. Okay, so the amount of the vapor and its vapor pressure, that depends upon what I said. So that depends upon the nature of the liquids. Now when you make the binary solutions of this, right? So binary solution means when you mix liquid A and B, then what happens? A plus B will be there in the liquid state. Okay, so solution we call now it is called as what? Solution, and it will be having what? The vapor form of both the liquids. Okay, I will take another color. Right. So when you mix, you will be having vapor form of both, and the vapor pressure exerted by over the surface of the solution will be of what? The vapor form of liquid A as well as vapor form of the liquid B. Both are going to exert the pressure. Okay. So now how much a particular vapor form is exerting the pressure over the surface, that depends upon what? Its mole fraction in the solution or its mole fraction in the gaseous phase we call, and that is given by the very famous, that is we call it as what? Raoult's law. Okay, so it is very important, Raoult's law. How we are going to define this? The partial pressure, okay, exerted by a particular gas is directly proportional to what? The mole fraction. The pressure exerted, the vapor pressure of a given liquid over the surface of the solution is directly proportional to its mole fraction. Okay, so then how we will give? So therefore PA is equal to, we write P naught A into XA, where P naught is what? Proportionality constant we will take, and that is what is the vapor pressure of the same liquid when it is in the pure state. Okay, pure solvent we call, or pure liquid. And similarly you take PA is directly, PB is directly proportional to mole fraction of B. So therefore PB is equal to P naught B into mole fraction of B we will take. And from Dalton's law we know that, what we know? So total pressure of any mixture of the gas or vapor will be equal to sum of the partial pressures. Here two components are there in the vapor form. One will be of liquid A, another will be of liquid B. So therefore always the total pressure is always equals to what? Partial pressure of liquid A, partial pressure of vapors of the liquid B we call. So therefore PA, if you substitute, what you will be having? P naught A into XA, mole fraction of A, plus P naught B into XB. So that is nothing but P total we call. Okay, so this is what we call it as what? Raoult's law. And always remember, if the interaction between A and B are as good as in the pure A and B, what interaction between A and B, if you have same interactions, if you find between A and B, then we expect what? A linear variation in the vapor pressure by changing the composition of A and B. Okay, and then it is called as what? Ideal solution we call. Okay, when the variation is linear, and that linearity arrives when the interaction between A and B is as same as the interaction between AA and BB in the pure state. Okay, if the interaction is not as good as in the pure state have between AA and BB in when you mix both between A and B, so then we call it as what? It is moving from ideality, or it is also said as what? Non-ideal solution. Okay, so we'll see that one. Ideal solution. The solution which obeys Raoult's law at all composition, then it is called ideal solution. Means, say for example, liquid A and liquid B, when you mix these two in any proportion, okay, like you can take 90-10 or 80-20, 50-50, any composition if you mix. So if it is going to the variation in the vapor pressure, if it is linear, or according to Raoult's law, what formula we have given, so P is equal to P naught A plus X A into plus P naught B into XB. So if it is varying accordingly, so then it is said to be what? Ideal solution. And for this ideal solution, always remember, enthalpy of mixing will be always equals to 0, and the change in volume will also be 0, because there is no increase in the volume or decrease in the volume when you mix the two liquids. Okay, so to make a ideal solution, right? So, and delta S will not be equal to 0. You should remember this. These conditions are very important for ideal solutions. Okay, so the next is from ideality, then how we will get the nature of the graph when you plot a graph for this ideal solution. Say A is having its boiling point as mentioned here, and B if it is having here. Okay, so then what happens for A? So as the composition, say for example, A is 100% here B is 100%, and as you move on, so then what happens? The concentration of B goes on in, so there it is B and A. So composition, varying compositions if you take, so then what happens? The vapor pressure goes on, changes of the solution like this, and this will decrease in this way, and you will be having the total pressure as P is equal to a linear variation we are going to observe. Okay, so this is the vapor pressure of A, this is the vapor pressure of B, and that is how it is going to vary as the composition, means concentration of A as it goes on decreases, so therefore vapor pressure also decreases, because mole fraction of that is going to decrease. Similarly, as you move from this side to this side, what happens? The mole fraction of the B decreases, so therefore vapor pressure also goes on decreases, mole fraction. Okay, so this is what we call it as what? Graph for ideal solution. Similarly, what is non-ideal solutions? We will say, very important exam point of view, state Raoult's law, and what are ideal and non-ideal solutions. They will ask for 3-mark questions, or just they will ask about what is ideal solution according to Raoult's law. So you have to draw the graph and you should explain, and you should give the conditions of enthalpy, volume as well as entropy. Okay. Similarly, we will look into non-ideal solution means what? Non-ideal solutions. Okay. So non-ideal solution means, now suppose when you mix liquid A, liquid B, so liquid A are there. So when you mix these two, so always it is not as A-B interactions will be, the interaction between A-B will not be as same as in the case of AA and BB. Okay, it is not with all the solvents. For ideal, again I will give the example. For ideal solution, you can take so benzene toluene as an best example. You should remember benzene toluene or bromobutane. You can take bromobutane and chlorobutane. So these are the two examples for ideal solution. Okay, you make note of this. So what do you mean this ideality means? So when I take benzene molecule, what type of interactions they have? Toluene molecules, what type of interactions they have? When we mix also, the same type of interactions they have, means neither one molecule will repel other molecule or one molecule will attract other molecule. So what type of interactions they have in the pure state, same interactions you will observe in the solution state also. Okay. So now, and it is always, we cannot expect from all the different binary mixtures. Okay. So it will not be same, right? So now AB interactions upon mixture of mixing of two liquids. Okay, liquid solution, liquid A, liquid B, when you mix, so A may repel with what? B. Repulsion they can do. Okay, we call it as what? Repulsive interaction we call. And another one is A may attract B. Okay, A may attract B means attractive interaction. Then compared to what? In the pure state. AA, what type of interactions they have? So when you mix those two, when then AB, if they are repelling with each other, so that happens when the nature of the two liquids is slightly differing from one another. So then there will be a repulsion, and if that repulsion happens, then what happens? There will be a deviation in the Raoult's law, and that deviation we call it as what? Positive deviation, because so the vapor pressure will be higher than expected. Vapor pressure is higher than what is expected for ideal condition. Okay. Similarly, if there are attractive interactions, if you have, so then what happens? The molecules will hold, A will hold B, B will hold A, and it will not allow the A to escape out or B to escape out. Means vapor form will be less and your vapor pressure will be, it will be lower than the expected one. So therefore your vapor pressure, this we call it as what? Negative deviation from the Raoult's law, and your vapor pressure will be low. Okay, and graphically we will represent this positive and negative deviation. Okay, and this we call positive, negative deviation. So when the interactions are repulsive, then we will see the positive deviation from the Raoult's law, and if there is attractive interaction between the components of the liquid, then there will be a negative deviation we see. Okay, so for any two liquids B and A binary mixture if you take, so this is what we expect if it is ideally behaving, right? Then if it shows positive deviation, okay, so then what happens? Your graph will be like this. Okay, and if it is showing negative deviation, you will be having graph like this. Okay, so this is negative deviation, this is positive deviation, and this is what? Ideal situation we call. And this is non-ideal with positive deviation, and this is non-ideal with negative deviation. Okay, so example for positive deviation, water and ethanol. These are going to show very high positive deviation from Raoult's law. So what is the reason for that, they may ask. So what is the reason means? So there what happens, the hydrogen bonding which are present in the water molecule is being broken by the ethanol molecule, leading to what? Escaping of the water molecules to greater extent. Okay, so that is an example for positive deviation. And negative deviation, you can take chloroform and acetone. Chloroform acetone is an example. So where what happens? The chloroform is going to do the hydrogen bonding with carbonyl oxygen of the acetone. Okay, HCl. Okay, anyhow, by inductive effect, the electron, it is having partial positive charge, partial negative charge, so therefore they will attract with each other, so therefore they will show negative deviation from the Raoult's law. Okay, so this is all about positive deviation and negative deviation in brief. Okay, and always remember, enthalpy of mixing will not be equals to 0. Okay, and the change in volume of mixing, always remember, greater than 0 for positive deviation, and volume change upon mixing for a non-ideal cell is less than 0, change in volume for negative deviation. These two in the non-ideal condition, you should remember. Okay, so the next is what azeotrope means. Okay, so there is a particular composition of the two binary components of the solutions. What they are having? Constant boiling. Okay, so they boil at a particular composition of two binary liquids having same composition of both A and B, okay, in vapor phase. So therefore they boil at a single temperature, okay, same temperature, and that constant boiling mixture we call it as what? Azeotropic mixture we call. Okay, and we will be having two different types of azeotropic mixtures. One we call it as what? Low boiling azeotrope. For example is your ethanol and water. So where it is 95%, means 95% ethanol and 5% will be water. And this mixture we cannot separate it, because what is the reason for that? So both the water as well as ethanol will boil at the same temperature. So hence it is not possible to separate. Always remember, azeotropic mixtures we cannot separate by simple distillation method. Okay, so this is the example for low boiling azeotrope. Similarly, another one we call it as what? High boiling azeotrope. Usually, which shows negative deviation from Raoult's law. Such mixture will be having what? High boiling what? Azeotrope. So example is 68% of HNO3 and water, 32% of water. It is an example for high boiling azeotrope, and this mixture you cannot separate it by distillation, because vapor form will be having same composition as that of in the what? Liquid phase. Okay, so this is all about ideal. Very brief I have explained here what is ideal and non-ideal solutions, what is Raoult's law. Okay, so this is all about Raoult's law, and it is very important. One question will be there on this, maybe problem, or they may ask what is Raoult's law, according to Raoult's law what is ideal solution, or according to Raoult's law what is non-ideal solution, what is positive deviation, what is negative deviation. So like one question will appear on this particular topic, you should remember, or at least 1 mark question will be there on azeotropes. Okay, so they may ask on this azeotrope. Okay, we will see that in the question part. Next important topic on which we expect more questions is colligative properties. Okay, so it is very important. Definitely one question will be there on this, at least for 3 marks. Okay, either you will get numerical problem or you will get some theory question on this, right? So we'll talk about this colligative property, the property of dilute solution containing non-volatile solute which depend upon the number of solute molecules but not on the nature of the solute is called colligative property. Colligative property. Okay. So the property of the dilute solution which depends upon containing non-volatile solute which depends upon the number of solute molecules but not on the nature of the solute molecule is called colligative property, and those colligative properties is lowering of the vapor pressure, okay, elevation in the boiling point, depression in the freezing point, and osmotic pressure. Okay, so we'll see one by one. Lowering of vapor pressure. So now you consider you have taken a pure liquid solvent, what we call, and it will be having certain vapor form accumulated over it when you take it in a closed vessel. So now it will exert certain vapor pressure that we call it as what P naught. And now what you do if you add a non-volatile solute to this, okay. So now what happens? The vapor form will be less at the given temperature, hence vapor pressure is also less. What is the reason for that? So the vapor form arrives by the escaping of the molecules from the surface. So therefore, as non-volatile solute, when you add to make the solution, okay, then what happens? They are uniformly distributed, hence some of the molecules will occupy at the surface and they won't allow or they suppress the evaporation of the molecules. Okay, so because of that reason, what happens? Vapor form will be less and vapor pressure is also hence decreased due to the presence of non-volatile solute in the solvent. So therefore, according to Raoult's law, the relative lowering of vapor pressure is given as P naught minus Ps, where P naught is vapor pressure of the pure solvent minus vapor pressure of the solution to the vapor pressure of the pure solvent is equal to, okay, so mole fraction of the what? Solute in the given solution. Okay, so that mole fraction how we will give? Number of moles of a solute to the total number of moles of what? Solute plus solvent. Okay, so we'll write P naught minus Ps divided by P naught is equal to N means we will take W2 by M2 means W2 is weight of the solute present in the solution and its molar mass divided by, in the numerator, this N term for dilute solution we will neglect it. Okay, we will not consider this one and we will take W1 by M1 where it is the weight of the pure solvent divided by its molar mass. Okay, so now when you rearrange this, you are going to get as P naught minus Ps divided by P naught, okay, which is equal to W2 M1 divided by M2 into W1. Okay, so this is how we are going to get the equation. And if you want to determine the molecular weight, we can determine molecular weight of the solute, that is M2 is equal to, so W2 into M1 divided by W1 into P naught divided by P naught minus Ps. Okay, so this is how we can determine molecular weight of the solute by using lowering of the vapor pressure. Okay, similarly, this equation is very important because question will appear on this for 3 marks. totally we'll be having 4 formulas, and on those 4 formulas, at least one problem we will be getting in the examination for 3 marks. Okay, you should remember this. This is one first formula in this colligative property, and second we will see that one. Elevation in boiling point. By the addition, we know that first we should know what is this boiling point means. When the vapor pressure over the surface of the liquid becomes equal to atmospheric pressure, then we call it as what? The temperature at which the vapor pressure becomes equal to atmospheric pressure is called boiling point. Now, upon addition of non-volatile solute, already its vapor pressure at a given temperature is low. So, therefore, what happens? Become its vapor pressure to atmospheric pressure, we have to raise its temperature little higher because already its vapor pressure is what? Low. So, that we call it as what? Elevation in the boiling point, and that we will give as Ts minus T naught. So where T naught is what? The boiling temperature of the pure liquid, and it is the boiling temperature of the solution. Okay. So therefore T naught or Ts minus T naught is always directly proportional to molality of the solution. Okay. How we will give? So the molality means number of moles of solute per kilogram of solvent. Okay. So therefore, so that is how we are going to represent, and this we take it as what? Delta Ts, which is equal to what? Kb. It is called as into m, small m. So the small m represents here what? Molality of the solution. So therefore, this Kb is called a proportionality constant. It is also referred as what? Ebuloscopic constant. Ebuloscopic constant, and it depends upon the nature of the solvent. Okay, so by this we can even determine the molecular weight. How we can determine? So you write like this: delta Ts is equal to, or you can call it as delta Tb, we can call it, okay, elevation in boiling point. So therefore Kb into molality means number of moles of solute. Number of moles of solute we can give like this: W2 by M2 divided by per kg of the solvent. If the solvent is given in terms of, okay, kilogram, then directly we can use W1. Or if it is given in terms of grams, then what you have to do? You have to divide that by 1000. Okay, when it is given. Both the formulas I will write. Okay. So delta TB is equal to KB into W2 into 1000 divided by W1 into M2. So therefore M2 is equal to KB into W2 into 1000 divided by W1 into delta TB. So this is the second formula that we have to remember in the determination of molecular. Definite question you will be getting on this particular formulas. Okay. So here one thing you should remember, this formula you have to use when the given solvent is in grams. The quantity of the solvent given, if it is in terms of grams, if it is there, then you have to use this formula. Or what you have to do, if it is directly given in terms of kilograms, okay, Kb into W2, okay, just W2 you keep it, and W1 into delta Tb. This is the another formula that what you have to use when already solvent is given in terms of kilograms. Okay, so if it is given in terms of grams, then you have to multiply that with 1000. If it is not given in terms of grams directly, if it is given in terms of kilograms, so then you have to use this particular formula. Okay, so this is how we can determine the molecular by using elevation in boiling point. Okay, then last one is depression in freezing point. So this is also once again related to the lowering of the vapor pressure. Okay, so depression in freezing point. Freezing point is represented as delta TF. Okay, exactly same way we are going to formulate this also. See here, delta TF. See, the freezing is a phase transition where what happens? Liquid condenses to solid phase. Okay. So, and this happens at atmospheric pressure. So, as it happens at atmospheric pressure, already your pressure is lowered because of addition of the solute. So, due to which what happens? You have to take to the still more lower temperature to what? Freeze the liquid into solid phase. So, therefore, that we call it as what? Depression in the freezing point, right? So, that freezing point, how we will give the temperature at which the freezing point of the pure solvent minus freezing point of the solution. So that we will give it as what? Delta TF. Okay. So therefore, delta TF, once again, it is also proportional to molality of the solution. Okay. So delta TF is equal to KF into molality of the solution. Exactly in the similar way, one thing you should remember, to remember this, one hint I will give. The formula for elevation in the boiling point and depression in the freezing point will be exactly same you will be having. Only thing is, in place of delta TB, you have to place delta TF. Okay, so that much if you do, so the same thing will be there. Because of that reason, I kept like that only. Just I will alter here only, right? So what we will do, so here Kf is called cryoscopic constant. Okay, it is called cryoscopic constant. And already you know what is M is molality, and this is a depression in the freezing point, right? So let us substitute the things. We will make it as Kf, Kf if you write. So this you make it Tf. Okay, rest thing will be same. Once again, if the in the problem, if it is given solvent in terms of kilograms, so then no need to use this 1000. In place of directly, you can put this formula. If it is given in terms of grams, then you have to use this particular formula. Okay, so you make it delta TF. That's it. Okay, why I have written like that only? The reason behind that is because the formulas are same. Only thing is you have to substitute in place of KB as KF, and delta TB in place of that you have to place delta TF. Okay, if the two temperatures are given, then you have to take the temperature, freezing temperature of solvent minus freezing temperature of the solution you have to take. So whereas in the case of lowering of vapor, this elevation in the boiling point, we will take a solution minus solvent we are going to do, right? So that difference you have to make out. The last property is osmotic pressure. So this is the third formula that you have to take into account, right? So and last formula, on these four formulas, definitely will be getting one question for 3 marks. Okay, you should remember that. All the last previous year question papers, if you open from 2014, so all the question paper will be having one problem on this particular formulas. Okay, then last one is osmotic pressure. See, what is osmosis? Let us clear this one. So if you take pure solvent or liquid, we can call, and another side, if you take any solution containing same solvent, and if you separate that with a semi-permeable membrane, which we call as what? Semi-permeable membrane. On this semi-permeable membrane, once again, you will be getting 1 mark questions, right? So this is again important. Semi-permeable membrane is the membrane which allows only the flow of the solvent molecules, but not the solute molecules. Those are called semi-permeable membranes. Okay. Example for we can take there are examples of natural semi-permeable membranes and artificial semi-permeable membranes. Artificial cellophane is there. Okay, and many others you can take. So this semi-permeable membrane is the one which will allow the movement of the solvent. Okay, not the solute molecules. If you place like this, then what happens? immediately the solvent molecule starts moving from its what? So the migration of solvent molecule from its higher concentration to its lower concentration, we call it as what? Osmosis. Okay. So now, or pure solvent you can take, or you can take dilute solution. Dilute one, you take concentrated solution. Okay. So then definition will be, defining will be very easy. So the movement of the solvent molecule through a semi-permeable membrane from a dilute solution to the concentrated solution, we call it as what? Osmosis. Okay. And as this solvent molecule migrates, then what happens during this migration? It is going to exert a pressure on the what? The semi-permeable membrane, and that pressure we call it as what? Osmotic pressure. Means, so the pressure with which the solvent molecule will migrate from dilute solution to the concentrated solution, we call it as what? Osmotic pressure. Once again, this property also depends upon only number of the solute molecules, but not on the what? Nature of the solute molecules, right? So how we are going to determine this one? Say for example, you can take its determination is once again important exam point of view. So you take your liquid and you separate both with a certain chamber, right? So you will be having like this, right? So there is a piston, okay? So how much pressure which it can withhold, okay, applying the pressure, that just stops the osmosis, we call it as what? So one side you take dilute solution, another side you take concentrated solution, okay? So how much pressure you have to exert, okay, to just to stop the migration of the solvent molecule from its higher concentration to its lower concentration, we call it as what? Osmotic pressure. Okay. It is related as it is taken as ever considered as if it is an ideal gas equation. Okay. PV is equal to nRT, like that we will take osmotic pressure pi into V is equal to nRT we will take. Okay. So pi is equal to N by V into RT, and we know that one N is nothing but what? Number of moles. Okay. So number of moles means how we will give? Weight of the solute molecule by molar mass, M2 into RT by V. So pi is equal to like this we will get. Just if you reshuffle this one, we will be getting M2 is equal to W2 by pi into V into RT. Okay. So by this formula, we can determine once again what? Molecular weight of the given solute present in the solution. Okay. So that is how by using osmotic pressure also we can determine the molecular weight. Then last important thing what you have to remember in this is reverse osmosis means what? Okay. So this reverse osmosis is a technique which is being developed to purify the salt water or concentrated water. Okay. So even if you take groundwater or if you take sea water, if you want to get the sweet water from that. Okay. So then desalination of the water we can do by reverse osmosis. Reverse osmosis meaning is what? If you apply the pressure, say here we are going to take pure water, okay, and which is being separated by the semi-permeable membrane, and here it is taken salt water or sea water or saline water we can call, and here we are going to apply the pressure over it. Okay, as you apply the pressure, then what happens? The movement of the solvent molecule will take place in the reverse direction, hence it is called reverse osmosis. If you relieve the pressure, then what happens? Solvent molecules will migrate from pure water to the salt water side. But when you compress it, so then what happens? Forcefully these molecules are made to flow into the pure water side, and this we call it as what? Reverse osmosis, and this technology is being used to purify the salt water. Okay. Then next is abnormal molecular weight. So now whatever the molecular weight we determine by using these colligative properties, sometimes what happens, it will not be same as that of corresponds to the molecular weight of the solute molecule, and then we call it as what? Abnormal molecular weight. Okay, it is referred as what? Abnormal molecular weight. And this abnormal molecular weight, how we are going to calculate? See, here it is being given by. Okay, so to include that, event of factor I is equal to. So abnormal, the difference in expected molecular weight of the compound, or we can call it as solute molecules. Solute, the difference between expected molecular weight of the solute and experimentally obtained molecular weight. Okay, so that we call it as what? Abnormal molecular weight. And how we are going to get this one? This we are going to get due to what happens? We are considering, say for example, I have added 10 molecules are there, say for example. So now what happens? These molecules in the given solvent, if they have tendency to associate with other molecule to form the dimers. Okay, we call it as one phenomenon called as association. And another one condition will be in the given solvent. Sometimes what happens? Molecule may dissociate. Say for example, if you take electrolyte NaCl, if you add, then what happens? It will be Na plus and Cl minus in aqueous solution. So we are expecting this together as one molecule in calculating the molecular weight, but it is present as two entities. When it is present in two entities, then what happens? Observed colligative property will be high. So observed colligative property will be high means molecular weight will be, calculated molecular weight will be low. Okay, so because of that reason, okay, so what we see is, so that leads to what? Getting abnormal molecular weight. One is association, another one is called dissociation. So to include this, okay, in the calculation of the molecular weight, so Ventoff has given a factor called I factor, Ventoff factor we call. This is very important. So what he called it as, I is equal to expected molecular weight divided by observed or determined molecular weight, observed molecular weight. Okay, so that we call it as what? I, or it is also defined as what? Observed colligative property divided by what? Expected colligative property. Okay, so now you should remember this. Always this I factor. Okay, so what information it will give is, suppose if the molecules are associated, then I will be less than 1. If the molecules are dissociated, then I value will be always greater than 1. Okay, if I value is equal to 1 means what? So the colligative the molecular weight determined will be what? Correct molecular weight, or it corresponds to the what actually molecular weight is possessed by the what? Solute molecule, right? So these are 3 points you have to remember, because they will ask question on this particular for 1 mark. Okay, you should remember about this. This is all about the brief revision of unit solution. Okay, already I have said it is having weightage 13 marks, and you should be careful about all these important things, right? And I hope I have covered many aspects of this solution, right? And apart from this, I suggest you to go for reading what textbook, as previously I have mentioned, sentence by sentence, just you read, because in MCQs, only thing is to you have to remember. Okay, so therefore, if you read once the whole chapter in the NCERT book, definitely we are going to solve the 2 questions carrying each 1 marks, because our mission is 70, 70, so therefore we should not leave single marks also. Okay, thank you for watching.